Welcome to the Wetland Hydrology training video for the Lentic AIM program. My name is Katrina Castro, and I'm an aquatic ecologist with Colorado Natural Heritage Program. This presentation will provide a general background on wetland hydrology, a description of wetland water sources, and the hydrology methods outlined in the Lentic AIM 2021 Field Protocol. Wetland hydrology is the most defining feature of wetland ecosystems. The hydrology of a wetland is largely responsible for the vegetation of the wetland. Since wetlands are typically wet for at least some of the growing season, this influences plant communities and favors those that are adapted to survive low oxygen levels in the soil. Wetland hydrology also influences the biological activity within the soil. Since soil saturation leads to anaerobic environments, soil microbes must adapt in the absence of oxygen. Over time, this can lead to the formation of hydric soil indicators. When we say wetland hydrology, we mean that wetland hydrology refers to the timing and extent of inundation or soil saturation and is a driving function that creates and maintains wetlands. Landscape position, climate, topography, surrounding land use, and soil permeability all influence the hydrology of a wetland. In this figure, you can see the general direction of water flow into and out of wetland environments. Inputs include groundwater inflow, surface water inflow, and precipitation. Outflows include groundwater inflow, surface water outflow, and evapotranspiration. As you can imagine, the position of a wetland on a landscape, the local climate, and the soil permeability of a given area all impact the movement and collection of water on the landscape. In this general example, you can see that the yellow arrow is pointing to an area where landscape position and soil permeability are not favorable for wetland hydrology to take place. The steep slope of the talus field, combined with the high permeability of the substrate, do not allow for sufficient water retention. In contrast, the area in the foreground, indicated by the red arrow, is much more conducive for wetland hydrology to take place. Its position on the landscape allows for a collection of both surface and groundwater inputs from the uplands, and we can assume that its gentle slope is much more capable of retaining those hydrologic inputs. Factors such as landscape position and climate are closely related to the primary water sources of a wetland. Generally speaking, all water sources can be categorized into groundwater, surface water, and precipitation sources. We will now discuss and define the different water sources that influence the hydrology of wetlands. Sites dominated by groundwater have high water tables and are often found at the base of slopes where groundwater from the regional aquifer discharges to the surface diffusely. Groundwater can also be a water source in basins with high water tables due to subsurface features such as shallow bedrock or glacial till. A seep or spring is a localized discharge point of groundwater. Use this water source to indicate a specific point source of groundwater discharge, such as a spring head. This water source typically occurs in conjunction with diffuse groundwater discharge. It may be tempting to record seep or spring as the dominant water source on sample plots, named after adjacent springs such as Coyote Spring or Willow Spring, but use the information you have gathered while at the monitoring plot to help inform the most appropriate water source. Sites influenced by alluvial groundwater typically occur in basins with local shallow groundwater that is hydrologically connected to a stream channel. In many cases, riparian areas and floodplains have shallow plant-available groundwater that seeps from the stream channel, also known as losing streams. Or flows underground towards the stream from regional aquifers, also known as gaining streams. Overbank flooding is where water has surpassed the banks of a stream or river. Riparian areas and floodplains adjacent to stream or river channels are often influenced by periodic or seasonal overbank flooding. Sites that are dominated by overbank flooding include stream and river systems prone to flooding events such as summertime monsoons and spring snowmelt. Streams and rivers with active and historic beaver activity, such as the system pictured here, are typically dominated by overbank flooding. In contrast to overbank flooding, stream inflow is reserved for terminal wetlands that receive inflow from a stream rather than overbank flooding that flows through the site. In most cases, stream inflow spreads out, pools, and infiltrates across the wetland to maintain high water levels in the soil. Wetlands with hydrologic processes dominated by a pond, lake, or reservoir all have a direct connection to an open body of water. Riparian and wetland areas located along the margins of ponds, lakes, or reservoirs can be tied to rising and falling reservoir levels via surface or groundwater. However, not all wetlands on ponds or lake margins are solely tied to the open water body, such as the wetland pictured in this example. Consider other water sources, like upslope groundwater discharge and fluvial or alluvial sources. Wetlands dominated by direct precipitation are restricted to areas with high seasonal or annual precipitation. Very high amounts of precipitation can support bog wetlands, which are saturated wetlands completely isolated from groundwater sources. To assign direct precipitation as a water source, consider whether direct precipitation is the wetland's predominant water source, not whether the wetland occasionally receives precipitation. As you can imagine, wetlands driven by precipitation are extremely rare in the arid West. Wetlands that rely on snowmelt are commonly found in the montane to alpine zones where slowly melting glaciers, snowfields, or snowbanks provide a consistent water source during the spring and summer. These wetlands almost exclusively occur in high elevation areas that receive significant amounts of snowfall over the winter. Wetlands fed by overland flow accumulate runoff from the upslope. The diffuse downslope movement of water over land that occurs when precipitation exceeds the soil's infiltration capacity. Examples of overland flow include depressions like playas or vernal pools that accumulate runoff after large rainfall events, and often have low permeability soil or bedrock that collect and perch water from immediately adjacent areas. Some types of wetlands are fed by alternative water sources that do not fall under the groundwater, surface water, or precipitation categories. One example would be wetlands that are formed and maintained by excess irrigation water applied to farmlands. The excess water flows downslope and accumulates into drainages or other low points. Irrigation canals can also seep on the downslope side. Pictured in this example, you can see where excess irrigation water has collected in the drainages, flowing away from nearby irrigation fields. This concludes the general hydrology and water sources portion of the presentation. For additional guidance on wetland water sources, refer to page 63 in section 5.3 of the Lentic AIM protocol. We will now continue into the hydrology and surface water field methods portion of the presentation. You can follow along in section 5.3 of the protocol and refer to Appendix G. Though hydrology is such a critical characteristic of a wetland, it can sometimes be the most challenging characteristic to determine in the field. The lentic AIM protocol considers hydrology a covariate method, meaning that it is used to help characterize the site for purposes of classification, stratification, or to determine a wetland's ecological potential. Hydrology information will be collected at all field sites sampled during the 2021 field season. The hydrology data collected with the lentic AIM protocol include determining water sources, recording surface water characteristics, taking note of any evidence of surface water, collecting channel dimensions, if applicable, and summarizing with a general hydrology description. At every lentic AIM site, you will determine a dominant water source and record any additional sources when applicable. When determining the primary water source of a monitoring plot, it is important to take into account the following: landscape position and watershed setting, regional wetland types, surrounding land use, topographic maps, historic imagery, and local climate data. It is also important to walk the entire site and take note of on-site water levels, flow paths, and plant communities. When selecting the dominant water source of a wetland, carefully consider the site's classification and general wetland type, as well as how the wetland likely formed. When determining water sources, it can be helpful to consider the physical setting of the wetland at the watershed scale. The position of a wetland on the landscape influences the source and movement of water within the wetland. In addition to landscape position, taking region and ecoregion into account can help to better understand what hydrological processes are typical of the greater area. The examples pictured here show the variability of groundwater flow direction across different ecoregions and the different types of wetlands that are more likely to result. As you can see, different ecoregions generally have different hydrologic settings and therefore support wetlands with different dominant water sources. Surrounding land use, especially groundwater extraction, can influence the seasonality of a wetland. Irrigation practices, including groundwater pumping, can cause changes to wetland hydroperiods. Wetlands adjacent to groundwater extraction activities may experience reduced water levels during the summer and increased water levels in the fall. Pay close attention to the water developments in the vicinity of your monitoring plot. Be sure to review climate data and be familiar with the recent weather before heading out on hitch. Pay particularly close attention to areas that may have received a precipitation event recently. Pictured here is a drought monitor for the 2021 spring. As you can see, much of the Great Basin and Colorado Plateau are in an exceptional drought, while the Middle Rocky Mountains are in a moderate to severe drought. Expect the intensity of your monitoring area's drought to increase throughout the course of the growing season. Once you have determined water sources, record if surface water is or is not present within the monitoring plot. As you can see, you will need to fill out different information depending on what is observed on the plot. If surface water is observed on the plot at the time of sampling, you will need to estimate the extent cover, estimate the predominant depth across the entire monitoring plot, and record the distribution of surface water and whether or not it is ponded or in small channels. You also need to observe and record several characteristics of the surface water, including any water surface occurrences such as oily sheens or algal blooms, the smell of the water, and the substrate below the surface water body. Further guidance on water surface characteristics can be found in the text box on page 66 of the lentic AIM protocol. You can also find guidance on water smell and substrate textures on page 67 of the Irrigation protocol. If surface water is not observed during the site visit, record its absence. As you walk the site, look for any evidence of recent saturation or surface water, such as aquatic invertebrates, drift deposits, drainage patterns, and surface soil cracks. Refer to Appendix G in the Irrigation protocol for a list of examples of applicable hydrology indicators. Be sure to record the observations using terminology consistent with the Army Corps indicators where possible. If one or more channels flow through the monitoring plot, you will need to record its characteristics. If there are multiple channels within the monitoring plot, take measurements on the widest channel. Channels may include small, stable stream channels, rivulets, or channels formed by headcuts and incisions in wet meadows. The first measurement you should collect is on the length of the channel through the plot, including meanders within the plot. If you need to estimate the length in the field, be sure to check the estimate in the office using GIS or recent imagery. In addition to length measurements, you will also need to measure the average width of the channel. Be sure to collect width measurements from the top lip of the channel rather than the water level. The water level may be above or below the top lip of the channel at the time of sampling. If channel width is variable, measure the width in up to 5 locations and record the average, as pictured here. In addition to channel width measurements, average channel depth measurements will also be recorded. Similar to the measurements taken on channel width, measurements on channel depth are taken from the top lip of the channel to the base of the channel. If depth is variable, measure in up to 5 locations and record an average. Measurements of water depth within the channel will also be collected. When determining water depth, be sure to collect from the center of the flow of water, where the channel is at its deepest point. All dominant channels observed within the lenthic aim plot need to have a minimum of 2 photos taken during the site visit. Additional details about the number and characteristics of small channels within the plot should be included in the general hydrology description. Here are some examples of channels found in wetland and riparian areas. Pictured on the top left is an example of a rivulet. On the right is an example of a small, stable stream. And at the bottom left is a vague channel that does not have a defined morphological feature. Measurements on channel lacking for morphology or a clear lip would not be collected, so no channel measurements would be taken on this stream or this small channel. At each site, you will need to take notes on the general hydrology of the sample plot. Make objective observations and take notes on anything that may impact the hydrology of the site. Include any overall notes on site hydrology, including inflows, outflows, seasonality, surface water patterns, wetland hydrology indicators, channels, and any hydrologic disturbances. The photos pictured here represent various hydrologic features of interest. Starting from the top left and moving right, we see head cut and resulting plunge pool along a small montane stream, a dry canal, likely has diverted water in the past, a spring snail, which is a species of interest in many field offices, evidence of recent beaver activity, and on the bottom row, an excavator and recent dredge pile, and a head cut erosional feature in an area of diffuse groundwater. Refer to page 70 in the protocol for an example of a general hydrology description. This concludes the hydrology overview and methods following the lentic game protocol. For further reference on the hydrology methods, please see section 5.3 of the lentic aim field protocol.